I'm Damon, and I'm going to be taking you through predicting ATP tennis matches with deep learning methods. I got the ATP tennis match data from this link. It goes from the year 2000 to 2023, including this year's Wimbledon, which was just last week. I removed the betting odds because initially I didn't have betting in mind, and I didn't want to use the bookie's data science without understanding it. It is valid information, but for another experiment. I removed matches where a player retired or had a walkover because it's not really predictable and not indicative of skill. I also changed the winner and loser columns to alphabetically map to player 1 and player 2 columns, since we shouldn't know who won before the match starts. And the other important thing is that I created my binary target variable player 1 wins. Here is the list of variables from the raw data that I decided to use. When I first started fitting models on this information, the performance was quite poor because the relationships to predict whether player 1 wins are far too intricate and subtle for the neural network to pick up on. As a result, through code, I created my own extra features, which helped the performance a lot. There's quite a lot here, but as a couple examples, I've added a historical win rate for each player up until that point in time, and also a head-to-head count if those players have played before. I've also only kept the names of the 200 players with the most matches in the dataset. Everyone else becomes other. Here is a look at the data, and these are the last 5 rows, being Wimbledon that happened last weekend. And the yellow column that you can see here is the target variable player 1 wins. The main thing from data analysis I wanted to show you is the variable's respective correlations with our target variable player 1 wins. You can see that variables from the raw data have little correlation to player 1 wins, apart from P1 rank and P2 rank, which will form the basis of our benchmark model. However, as you can see on the right-hand side, the features that I have engineered provide more relevant information for the neural network to work with. Now for the benchmark model, it's very simple. The player with the higher rank wins, and this gives us an accuracy of about 65%. And a loss of about 5.3. My sequential model is a traditional feed-forward neural network with 2 hidden layers and a dropout layer after each for regularization. The dropout layer creates a random chance for each node within the layer to deactivate. This helps the model learn more generally and prevent overfitting. For this model, categorical variables were 1 hot encoded. My functional model is a deep and wide neural network which handles categorical and numerical data in a unique way. I've separated these categorical variables on the left to be embedded and then passed along with numerical data through deep hidden layers to capture more complex relationships. I've done this because surface specialists such as clay or grass specialists are huge in tennis, so I wanted to see if putting these variables together could allow the model to learn this. This model also benefits from a wide path, which directly connects my continuous variables to the output layer, facilitating simple relationships. So the combination of a wide and deep architecture helps this model to capture both simple and complex patterns in the data. As for results, it may seem disappointing that my accuracy is not that much better than the benchmark, but some reflection made me realize that I was somewhat spoiled rotten by the over 90–95% accuracies I was getting in my story walls. Firstly, those datasets were prepared with machine learning in mind, and secondly, if I could predict tennis matches with 90% accuracy, I wouldn't be here. It's also important to see that the increase in accuracy isn't negligible. A 2.5% accuracy boost represents an extra 1,500 matches predicted correctly. I didn't initially have betting in mind, but from that perspective, that level of accuracy boost makes a huge difference to profit. Perhaps with some extra hypertuning or feature engineering, I could bump up the accuracy a little more. It also goes to show that accuracy isn't the best metric of a model. As you can see, loss is significantly better in the neural network models. You might not want a model to just predict who wins, but also to tell you the probabilities of each player winning. As you can see here, in both models, for each match, the model will give you its confidence for player 1 to win. I trained my feed-forward network to be a bit more general, which makes it more conservative in probability predictions, centering 50-50. I trained my more complex, wide and deep model to learn patterns on surfaces, so it's a bit more bold in taking one player's side. This may be why it has a higher accuracy, but a higher loss value. Thanks for watching.